Slide 1 Introduction. Greetings, students. Today we embark on an exploration of an intriguing problem from LeetCode, specifically Problem 217. This challenge invites us to delve into the realm of integer arrays, prompting us to ascertain whether any duplicates exist within a given list of integers. The input we will be examining comprises an array that may include both positive and negative integers, with its length subject to variability. Our task is elegantly straightforward. We must inspect this array for any repeated integers and return a Boolean value, true should duplicates be discovered, and false if all integers remain unique. To illustrate, consider the example input, 1, 2, 3, 1. The output in this case is true as the integer 1 appears twice, indicating the presence of a duplicate. Grasping this problem is pivotal, as it lays the foundation for understanding key concepts related to data organization and computational efficiency. Let us delve deeper into this fascinating challenge. A hash set is a powerful data structure that stores unique elements, which means no duplicates are allowed. Think of it like a collection of distinct toys in a toy box. Each toy is different and can be easily found when you want to play with it. The magic behind a hash set lies in hashing. When you add an element, a hash function transforms that element into a unique index in an underlying array. This index tells the hash set where to store the element, allowing for quick access. Because of how it manages storage, operations like adding, removing, or checking for an element can often be done in constant time, or O1. This efficiency makes hash sets ideal for situations where you need to rapidly check for unique items, like tracking user IDs on a website. However, sometimes multiple elements might hash to the same index, a situation known as a collision. To handle this, hash sets use strategies like chaining, where each index points to a list of elements that hash to the same index. This ensures that we can still maintain uniqueness and access elements quickly. In summary, hash sets are essential for efficiently managing collections of unique data, providing the speed and reliability needed for complex data management tasks. Let's dive into the function defined here to demonstrate how a hash set works. The goal of this function, unique elements, is to extract unique elements from a list. First, we initialize an empty set called unique set. Think of a set like a special container where duplicates don't exist. If you try to add something that's already in it, the set just ignores it. Next, we loop through each element in the input list. For every element, we attempt to add it to our unique set. If the element is already there, it won't be added again, ensuring that our set only keeps unique values. Finally, we convert our set back into a list to return it. In the example provided, when we input a list with repeated numbers, the output will be a list of just the unique numbers, showcasing how effectively a hash set manages duplicates. This method is efficient and straightforward, making it a great choice for solving problems involving uniqueness. Iteration is a fundamental concept in computer science that involves repeating a set of instructions until a specific condition is met. Think of it like a chef following a recipe. Each step may need to be repeated, like stirring a pot or adding ingredients, until the dish reaches perfection. In programming, we use loops to facilitate this repetition. Loops allow us to execute a block of code multiple times, each time potentially with different inputs or states. This is crucial for tasks like processing elements in a list or performing calculations over and over again. The beauty of iteration lies in its ability to simplify our code. Instead of rewriting similar code for each task, we can use iteration to keep our programs concise and easier to manage. For example, when traversing an array or running simulations, iteration ensures our solutions are not only efficient, but also more readable. At its core, iteration begins with a starting point. A condition determines how long the repetition continues, and an update mechanism modifies the state, often incrementing a counter. The loop checks the condition, executes the code if true, updates the state, and repeats this process until the condition is false. Mastering iteration is vital as it lays the groundwork for more advanced programming concepts and algorithms, enabling us to tackle a wide array of problems effectively. Let's explore how we can double each element in a list using a Python function. First, we define our function named doubleElements, which takes in a single parameter called input list. This is where we'll pass the list of numbers we want to work with. In step 1, we initialize an empty list called result. Think of this as an empty container where we'll store our doubled values. Moving to step 2, we use a for loop to iterate over each element in the input list. Imagine going through a box of toys and picking each one up. For each toy, or in this case, each number, we double its value by multiplying it by 2. We then add this doubled value to our result list. Finally, in step 3, we return the result list, which now contains all the original numbers doubled. This function demonstrates a simple yet powerful concept of iteration, allowing us to efficiently process each element in a collection. Array manipulation is a foundational concept in computer science focused on modifying the elements of an array. An array is essentially a collection of items, all of the same type, organized in a fixed size and sequentially. Think of it like a row of lockers, where each locker can hold one item and can be accessed directly by its number. When we talk about array manipulation, we refer to actions such as inserting, deleting, updating, or rearranging these elements. This is crucial because many algorithms, particularly those for sorting and searching, depend on the efficient manipulation of arrays to operate quickly. In practical terms, you often use loops to go through each element of the array. For example, if you want to change the value of an element, you simply access it using its index and assign a new value. More advanced techniques like slicing, merging, or partitioning can help in organizing data effectively. Mastering these skills is essential for success in areas like data analysis and software development, where how you handle data can greatly influence performance. The function we see here is designed to double each element in an array. Let's break it down step by step. First, we initialize a new list called doubled, which will hold our results. This is like getting a fresh piece of paper where we will write down our answers. Next, we iterate over each element in the input array, R. Think of this as going through a line of boxes where each box holds a number. For each number we find, we double it, which means we take that number and multiply it by 2. We then add this doubled number to our new list, doubled. This process is repeated for every item in the original array. Finally, we return the new list of doubled elements. So if our input was 1, 2, 3, our output would be 2, 4, 6. This demonstrates how we can manipulate data in arrays effectively. To solve LeetCode problem 217, we start by understanding that we need to check if there are any duplicate elements in an array called nums. If any number appears at least twice, we should return true. Otherwise, we return false. Next, we choose a data structure, a set. This is ideal because it allows us to store elements and check for their presence in constant time, on average. So we begin by initializing an empty set named scene. Now, we iterate through each element in the array. For each number, we first check if it's already in the scene set. If it is, we have found a duplicate and we return true. If it's not in the set, we add it to scene. After completing the loop without finding any duplicates, we return false. The time complexity here is O(n), as we make a single pass through the array, and the space complexity is also O(n), in the worst case if all elements are unique. Here's a quick look at the Python code that implements this logic. By following these steps carefully, you can effectively determine if duplicates exist in the array. Today, we will explore LeetCode problem 217, which challenges us to determine whether any integer in a given array appears at least twice. The solution requires us to efficiently detect duplicates in the array. Key constraints include a length of up to 100,000 elements and integer values ranging from -1 billion to 1 billion. These constraints suggest that our approach must balance time complexity with space efficiency to handle large data sets effectively. Let's delve into potential strategies for solving this problem. The provided Python code addresses LeetCode problem 217, which requires us to determine whether a list of integers contains any duplicates. The function contains duplicate uses a set, a data structure known for its efficiency in checking membership, to solve this problem. When the function is called, it starts by creating an empty set named scene. Think of this set as a basket where we'll keep track of the numbers we've already encountered in the input list, nums. As we loop through each integer, num, in nums, we check if num is already in the seen basket. This membership test is quick, with an average time complexity of 01 for set operations in Python, allowing us to efficiently spot duplicates. If we find that num is already in scene, we return true, indicating a duplicate has been found. If not, we add num to our basket for future reference. If the loop finishes without finding any duplicates, the function returns false. This method is optimal, with a time complexity of on, where n is the number of elements in the list. Using a set not only improves our performance, but also simplifies the logic, clearly showcasing effective algorithmic principles. In this slide, we focus on the time and space complexity of LeetCode problem 217, which deals with finding duplicates in an array. First, let's discuss time complexity. The algorithm operates in on time, meaning it makes a single pass through the array. This is similar to scanning a bookshelf to find a specific book. You only need to look at each book once. Here, n represents the number of elements in the array, so if we have 100 books, we check each one, resulting in a linear relationship between the time taken and the number of elements. Next, we consider space complexity, also on. In the worst-case scenario, if there are no duplicates, we may end up storing all n elements in a set or hash table to keep track of what we've seen. Think of this as needing a notebook to jot down all the titles you've checked. If you wrote down every title, you'd use space proportional to the number of books you looked at. In summary, the algorithm efficiently balances time and space, making it effective for this problem.